In 2004, Dubai announced a building so tall that many engineers genuinely believed it could not be built. Not because it was expensive or complicated, but because the laws of physics themselves started becoming a problem. This is the story behind the incredible construction of a masterpiece, Burj Khalifa. By the early 2000s, Dubai had a problem that most cities would kill to have. Oil money was flowing. A skyline was rising from the desert, and the world was starting to pay attention. But Sheikh Mohammed bin Rashid Al Maktoum understood something that most leaders in his position wouldn't have admitted. The oil was going to run out. And when it did, Dubai needed to be something more than a city built on fossil fuel. It needed to be a brand, a destination so iconic, so visually undeniable, that people would fly across the world just to stand at its base and look up. That ambition needed a symbol. And the symbol they chose was a skyscraper so tall that workers at its peak experienced sunrise 45 minutes before the people standing at its base. A building that broke dozens of world records before it ever opened its doors. A structure so far beyond anything previously attempted that engineers couldn't borrow from what already existed. They had to invent almost everything from scratch. When construction began in 2004, the tallest building on Earth was Taipei 101, stood at 509 meters. What Dubai was planning was 828 meters, 60% taller than anything human beings had ever built. And on the 4th of January 2010, after 6 years of solving problems that had no textbook answers, the Burj Khalifa opened to the world. But the problems, as you'll see, started arriving before a single beam was ever placed. Challenge number 1, the wind. When you're building something that tall, wind stops being a background consideration and becomes one of your most dangerous enemies. A conventional rectangular skyscraper at 828 meters would experience wind pressure so intense and so consistent that it would begin to sway in a rhythmic, self-reinforcing cycle. A phenomenon called vortex shedding, where the wind essentially synchronizes with the building's own natural frequency and starts amplifying its movement. Left unchecked, that kind of oscillation can cause structural fatigue and eventually catastrophic failure. The engineering team spent a long time studying this problem, and the answer they landed on came not from existing skyscraper design, but from nature. Architect Adrian Smith drew his inspiration from a regional desert flower called the Hymenocallis, also known as the spider lily, whose 3 petals extend outward from a central core in a perfectly balanced, spiraling geometry. Taking that exact principle, they designed the Burj Khalifa with a Y-shaped 3-winged floor plan that spirals and tapers continuously as it rises, with each section stepping inward at 27 separate setbacks on the way up. What this does is constantly present a different face to the wind at every level, so no coherent vortex can ever fully develop. The result is a structure that, even at full height, sways no more than 2 meters in either direction, which for something standing 828 meters tall in the open desert is a genuinely extraordinary achievement. Solving the wind, though, was only the beginning, because directly beneath the site, the ground itself was hiding a completely different kind of problem. Challenge number 2, the foundation. Dubai is built on desert, and what lies beneath that desert is not the kind of ground you want to anchor the world's heaviest building into. Below the surface, you find loose sand, soft and porous limestone, and groundwater that is heavily saturated with sulfates, a naturally occurring chemical compound that, when it comes into prolonged contact with standard concrete, slowly breaks it down from the inside. For a typical building, this might be manageable. For a structure placing roughly 500,000 tons of load onto the earth, it was an existential problem. The solution required engineering on 2 fronts simultaneously. First, the team drilled 194 foundation piles, each 1.5 meters in diameter and sunk 50 meters deep into the ground, giving the structure something solid and deep enough to grip. But the piles alone weren't enough if the concrete filling them was going to be chemically attacked over time. So the engineers developed a completely custom concrete mix, a high-density, sulfate-resistant formula that had to be tested and verified continuously throughout every pour to make sure its composition remained consistent. The foundation raft sitting above all of this, a single continuous slab of concrete 3.7 meters thick, was poured in just 12 uninterrupted shifts, running day and night. And because concrete generates significant heat as it cures, cooling pipes were embedded throughout the slab and temperature sensors monitored every section in real time, keeping the internal heat balanced and preventing cracks from forming as it set. A single thermal imbalance, a single undetected crack forming in that curing process, and the foundation of the tallest building in the world would have been silently, invisibly compromised. With the ground finally secured beneath them, the team now had to figure out how to get thousands of tons of concrete all the way up into the sky. Challenge number 3, pumping concrete to the sky. This is a challenge that sounds simple until you actually think about what it involves. Concrete is an incredibly dense, heavy liquid. Pumping it horizontally across a construction site is manageable. But pumping it vertically, fighting gravity the entire way, through pipes stretching hundreds of meters into the air, is a completely different problem. The higher you go, the more the concrete wants to separate, lose pressure, and begin setting inside the pipe before it ever reaches where it needs to go. At the time the Burj Khalifa was being built, no pump on Earth had ever successfully delivered concrete to anywhere near that height. So the team worked directly with pump manufacturer Putzmeister to engineer an entirely new class of pumping system, the BSA 14000 SHPD, purpose-built for this project and capable of generating extraordinary pressure to push concrete upward continuously. In parallel, they reformulated the concrete mix itself specifically for pumpability, reducing its viscosity without sacrificing its structural strength. And all major pours were scheduled during the nighttime hours, when Dubai's temperatures drop and the concrete stays workable for longer. When the project was complete, the Burj Khalifa held the world record for the highest concrete pump pour ever achieved. And that record still stands today. Getting the concrete up was done, but once the glass cladding started going on, a crisis of an entirely different kind began to unfold. Challenge number 4, the glass that was cooking the building. The exterior of the Burj Khalifa is covered in more than 103,000 square meters of glass, a vast gleaming skin that makes the building one of the most visually striking structures on Earth. The problem is that Dubai regularly sees summer temperatures above 50 degrees Celsius, and glass by its very nature is extraordinarily good at trapping and concentrating heat. When the thermal analysis came back on the early designs, the numbers were alarming. Interior temperatures on the upper floors would be difficult to control, and the energy required to cool the entire building, with its hundreds of hotel rooms, nearly 1,000 private residences, offices and observation decks, would be so enormous that it threatened to make the whole project financially unviable to operate. The engineering response was layered and carefully considered. Every glass panel was treated with a high-performance reflective coating, specifically designed to block infrared radiation, the part of sunlight that carries heat, while still allowing visible light through. The panels were angled differently at different heights to redirect direct solar gain away from the building's interior. And, on particularly vulnerable sections of the facade, a double-layer curtain wall system was installed, creating a thermal buffer zone, essentially a pocket of air, sitting between the outer glass and the building's interior envelope. Together, these measures reduced solar heat gain by close to 50%. Without them, the Burj Khalifa would have been almost impossible to cool economically. But here's the thing nobody expected. Solving the heat problem accidentally revealed a resource hiding in plain sight. Challenge number 5, water from thin air. Because the glass surface of the building is kept significantly cooler than the hot, humid air surrounding it, the exterior of the Burj Khalifa sweats constantly and in remarkable quantities. Warm air hits the cooled glass, loses its ability to hold moisture, and deposits condensation across the surface of the building every single day. When engineers calculated the annual total, the figure was almost hard to believe. Approximately 15 million gallons of condensation collecting on the exterior of the tower every year. Enough to fill around 20 Olympic-sized swimming pools. Rather than treat this as a nuisance to be managed or a runoff problem to be solved, the team designed a collection system that channels every drop of that condensation through a dedicated drainage network and delivers it directly to the irrigation system serving the landscaping around the building's base. The world's tallest tower, standing in the middle of one of the world's most water-scarce environments, harvests its own water supply directly from the desert air, It's one of those engineering solutions that feels almost too elegant to be real. But as beautiful as the exterior solutions were, deep inside the building's core, a mechanical problem of a very different kind was still waiting to be solved. Challenge number 6. Lifting the spire. The spire, sitting at the crown of the Burj Khalifa, stretches 242.6 meters above the building's roof and is made of more than 4,000 tons of structural steel. It is the feature that, more than anything else, defines the building's shape against the Dubai skyline, and it could not simply be constructed in place the way the floors below it were. It had to be assembled in sections at level 156, already some 600 meters above the ground, and then hydraulically jacked upward into its final position piece by enormous piece. There was no crane in the world capable of lifting sections of that weight and scale to that height from the outside, so engineers assembled the spire from within the building's own core, using a system of hydraulic jacks, cable clamps, and roller guides to raise each section incrementally until the full 242.5 meters of steel stood in place above the roof. But the mechanical challenge of the lift itself was only part of the problem. At 600 meters above sea level, the wind is not the steady, predictable force it is at ground level. It is erratic, powerful, and capable of swinging a multi-ton steel section with enough force to cause serious structural damage or kill the workers guiding it into position. Every major lift had to be planned around meteorological data, with teams monitoring wind readings around the clock and waiting, sometimes for days, for a window stable enough to proceed safely. Workers operated at heights that most human beings will never experience in their lives, making precise manual adjustments to steel sections that outweighed anything they could physically resist. When the final piece of the spire locked into position, the Burj Khalifa officially became the tallest man-made structure in the history of human civilization. But the building still wasn't ready to receive the world, because moving thousands of people efficiently through 163 floors every single day required an elevator system unlike anything that had ever been built before. And solving that problem turned out to be far more complicated than most people ever realize. Challenge number 7. Getting people up there. 163 floors is a long way to travel, and moving thousands of people efficiently up and down a building that size requires an elevator system, unlike anything that had existed before. The fundamental problem is one of physics and weight. If you run a single elevator shaft, the full height of the Burj Khalifa, the steel cable required to reach the top becomes so long and so heavy that its own weight exceeds the load the elevator itself is designed to carry. The whole system collapses under its own mass before it moves a single passenger. The solution was to abandon the idea of full-height elevators entirely and instead divide the building into distinct vertical zones, each one served by its own independent elevator system. Passengers transfer between zones at sky lobbies, intermediate floors where you switch from one elevator bank to another to continue your journey upward. The high-speed elevators themselves travel at 10 meters per second, and to prevent the cables from developing dangerous oscillating vibrations at resonant frequencies, the kind that could, over time, fatigue and snap the steel. Every shaft was fitted with a rope sway monitoring system that had never been built for any previous project in the world. What makes the Burj Khalifa genuinely extraordinary isn't just its height. It's the fact that almost every significant challenge in its construction had no established solution when work began. The engineers and builders who delivered this project didn't arrive with a proven playbook. They invented the playbook as they went, under enormous pressure, in one of the most demanding climates on Earth. New concrete formulas, new pump systems, new glass technology, new elevator logic, new crane engineering, all of it developed specifically because this one building demanded it. The Burj Khalifa stands today not as proof that we were ready to build it, but as proof that the people behind it refused to accept that we weren't.